Gravity signals of the Earth's tides are measured worldwide. Here you see an example from the Black Forest Observatory, BFO. Clearly, the diurnal and semi-diurnal tidal periods are visible. The Earth is rotating within the forcing gravitational field of Moon, Sun and planets, and thus these signals are consistent with the forcing acceleration which can be computed from the position of the celestial bodies. One part of the gravity signal is the lunar tide M2, primarily caused by the Moon with a period of approximately 12.4 hours. It has the highest gravity amplitude of the semi-diurnal Earth tides. If it is compared to the forcing acceleration in detail, differences become obvious. This figure shows the temporal changes of the response of the Earth to the M2 forcing for different stations in Europe. Irregular variations are visible in the analyses. Similar variations are apparent at some of those gravimeters, for example at BFO and ST in Strasbourg. Thus, the deviations from the expected response of Earth are no local effects. But what is their origin? Hello and welcome. In this video I will talk with geophysicist Eva Schroth about her research field of tidal analysis. Tidal analysis allows to investigate temporal variation of tidal parameters on Earth. You will learn what the tidal parameters are, how they can be estimated, and what kind of analyzing methods are used to explain the variations over time. This can help to better characterize the gravitational deformation of the Earth. Gravimeters measure variations of the gravitational acceleration over time. Using those measurements, geophysicists analyze the Earth's tides. They want to investigate how the Earth responds to the forcing gravitational field. This property is called the Earth's admittance. They do this for so-called wave groups. A wave group sums the Earth's tides in defined frequency bands. The lunar tide M2 I showed you in the beginning is one such wave group. This sketch illustrates the variation of the gravity signal of M2 over time. When this is compared to the theoretical external forcing field, a discrepancy occurs. This discrepancy is due to the deformation of the Earth in response to the forcing and is described using the gravimetric factor and the phase. The gravimetric factor is an amplitude factor delta defined as ratio of measure to exciting acceleration. The phase phi accounts for the phase shift between measured signal and forcing. The gravimetric factor and the phase are called the tidal parameters. The variations I showed you in the beginning were such variations of the gravimetric factor. How were these variations observed and how can they be explained? Geophysicist Eva Schroth will explain this to us now. Hi Eva.
Hi.
Before we talk about the reasons of the observed variations, could you please explain how you determine the time dependence of the tidal parameters and how they vary?
The tidal parameters are estimated with tidal analysis for a set of wave groups. If we are interested in the temporal behavior of the tidal parameters, we apply tidal analysis to a shorter time window out of a longer data set. This is called moving window analysis. Then the tidal parameters are plotted over time. Here I show a simplified sketch. The curve shows the time-dependent admittance factor of Earth's response to the forcing of one wave group. This deviation from the constant factor indicates that we miss significant effects in the analysis. Thus, the theoretical signal is scaled differently depending on the position of the time window. As a consequence, the tidal parameters vary with the beat frequency of the wave group.
We saw that the tidal parameters vary over several months to years. Can this be due to changes within the solid Earth and thus the admittance of the Earth's body to tidal forces?
The admittance of the Earth can change if the elastic properties of the Earth would change. We know from geodynamics that geological processes can change the properties of the Earth, but this would happen on geological timescales like hundreds, thousands or millions of years, much longer than our time series here, and it would be unlikely to be periodic.
But what can cause the variations instead? In the beginning I showed the similar behavior of gravimeters in a distance of around 100 kilometers. These are no local effects.
That's right. Local effects are usually non-tidal signals like the subsurface hydrology. The similarity of the variations at all the European stations indicate that they are influenced by the same source. Originally, we modeled the data including a layered 1D model of the solid Earth and the measured air pressure in tidal analysis. The oceans, however, are not included primarily. But especially the oceans have a strong contribution at all tidal frequencies because of the ocean tides. They can influence nearby gravimeters in a similar way. That means the gravitational loading of the ocean is changing with time and thus has a strong influence on gravity. Additionally, the admittance of the Earth to tidal forcing is not constant in time. The amplitudes of the M2 frequency, for example, show an annual variation much stronger than it would be expected from the forcing alone. Therefore, the amplitudes and phases within the wave group always differ from the expected values.
So the ocean tides influence the Earth tides. How do you get information on ocean tides?
If we want to take the oceans into account, we need information about them. The difficulty is that there are no measurements of the oceans with a sufficiently high spatial and temporal resolution. Tide gauges are restricted to coasts and islands, while satellites need several days until they pass the same point again. Satellite data therefore suffers from temporal aliasing. There are ocean models which include satellite data, and they are able to predict the time-independent part of the M2 amplitude quite well. They assume the tidal amplitude to be constant and therefore are not able to account for temporal variations of the amplitudes. That's why I'm using sea surface heights predicted by time-stepping, non-linear, non-stationary ocean models. Usually they do not match the real oceans as well as satellite-based models regarding the stationary part of the M2 amplitude. However, they potentially contain the causes of temporal variations of tidal parameters.
I see. And how do you include those informations in your analysis?
I calculate the loading the ocean model would cause and add it to synthetic Earth tides. The synthetic data is then analyzed exactly as the measured data and the results are compared. Using synthetic data instead of correcting the measurements has a major advantage. Namely, we can make sure that the observed variation is caused by the ocean and not by some other effect which was not taken into account previously. Finally, the amplitudes of the variation of the M2 tidal parameters are of the same order as the variations we obtain from measured data and additionally have a similar shape.
And what can we learn from this result?
Since a while it was assumed that the oceans cause the temporal variations of the M2 tidal parameters. This is now the first time that we can show that the loading of the ocean masses is able to produce temporal variations of the correct amplitude and frequency. Here you see this for various gravimeters in Europe. So we can explain to a certain extent the long-term variations of the gravimetric factors from the beginning. On average, they are about 1.18 and vary with time. They express the amplitude of the recorded signal, which is amplified with respect to the forcing signal. About 16% result from a deformation of the entire globe due to the tidal forces. The rest of about 2.5% primarily results from the loading of displaced water in the oceans, giving a total factor of about 1.185 for the M2 tide. As well, we searched the cause of its temporal variation in the oceans. And since we know this now, tidal analysis can be used to evaluate non-stationary ocean models by their gravity effect. We have shown that the very small temporal variations of the ocean response can be recorded by superconducting gravimeters. With that knowledge, gravity data could possibly be used to study ocean response to global climate change, ocean warming and sea level rise.
So what is the next step in your current work?
Up to now, we used global ocean models. One would maybe expect that the masses, which are close to the superconducting gravimeter, have a larger contribution to the total effect. But also the amplitudes and phases of the variation of the different contributions are important. We want to study which regions of the global ocean have to be taken into account to explain the observed variation at a certain station sufficiently well.
Okay. Eva, thanks for these explanations of your work.
You're welcome.
In this video, you learned how tidal analysis is used to determine the tidal parameters of gravimetric factor and the phase shift. Eva Schroth explained how this is done using a moving window analysis. She showed how the variations of the tidal parameters can be explained by gravitational ocean loading and that the analysis of those tiny signal variations may help to better understand the ocean's response as a consequence of climate changes.
Bye.